If you serve multiple customers, here is a simple isolation pattern that prevents retrieval and caching from mixing tenant data. Most multi-tenant systems accidentally leak one customer's data into another tenant's results. Today, you will understand a small set of guardrails that stop that leakage and still let you use fast retrieval and caching. By the end, you will be able to spot the leak, isolate queries, and make caches tenant-aware. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Multi-tenant retrieval leaks show up in real workflows. You build a vector or text index for customer documents and let a model fetch context. If you do nothing, a search for the same phrase can return a different customer's document. Success means the current customer only ever sees their own documents, and caches never hand back another tenant's result. The idea is simple. Enforce a tenant namespace at every stage. Store IDs with a tenant prefix, filter queries to that prefix, rank only within the scoped set, and cache under a composite key that includes the tenant. This keeps retrieval and cache entries partitioned. A tiny change at each step buys strong safety without redesigning your whole system. We will build a minimal toy pipeline that shows the common leak, then fix it in 4 steps. You will see a naive search that mixes tenants, then a tenant filter, a tenant-aware ranker, a tenant-scoped cache key, and finally, a proof that an unsafe cache entry is ignored. The code is small, and the concepts map directly to real systems. This snippet shows a naive retrieval that mixes tenants and leaks data. The dictionary docs uses tenant-scoped IDs like T11 and T21, but results is computed by searching all values for the query queue without any tenant filter. The variable tenant represents the active customer session. Here, T1, the expression leak, checks whether any returned ID does not start with a tenant prefix, which would indicate cross-customer retrieval. By printing leak detected, we confirm the problem exists and needs a guard. Now we will narrow the view to only the active tenant. This snippet isolates retrieval by filtering to a tenant namespace first. The dictionary scoped is built by selecting only docs whose IDs start with the active tenant prefix, effectively creating a per-tenant view. The list hits, then searches within that narrowed view for documents containing the query. Sorting the results makes the behavior deterministic and easier to debug. The printed hits count confirms that only tenant T1 documents are considered now. Next, we will add simple scoring and pick a top set. This snippet ranks tenant-scoped hits and selects a top K result. The set tokes holds the query tokens, and scored pairs each doc ID with a simple token match score inside the scoped view. Sorting scored in descending order yields ranked IDs, and top picks the top K results. Increasing top K returns more tenant-isolated results, which may improve recall, but add latency and cost downstream. Decreasing top K tightens precision and reduces work, useful for quick responses and guardrails. Now, we will add a cache that respects tenant boundaries. This snippet adds a tenant-aware cache key to prevent cross-customer hits. The dictionary cache stores retrieval outputs, and key concatenates tenant and query, forming a namespace-aware identifier. Writing top to cache under this composite key ensures that different tenants with the same query do not collide. Reading cached retrieves the value for the current tenant only. Printing cache key shows the scoped key used for safe lookups, which is essential for multi-tenant correctness. Finally, we will show why that composite key matters by simulating a poisoned cache entry. This snippet proves cache isolation and guards against poisoned entries. The variable unsafe key simulates a buggy cache that uses only the query as a key, and a conflicting value from another tenant is inserted to mimic cache poisoning. The lookup res uses the scoped key from earlier, so it ignores the unsafe entry and falls back to the correct tenant result. The check OK asserts that all returned IDs match the current tenant prefix. The printed isolation OK confirms the cache design block's cross-tenant retrieval. This toy flow maps cleanly to production. In a real system, the tenant prefix might be a UUID, the scorer a vector similarity, and the cache a distributed store. The same pattern still holds. Namespace IDs, filter before you search, rank inside the scope, and key the cache with tenant plus query. Recap: it is a pattern for tenant isolation in retrieval and caching. Use it when you serve multiple customers from one index or cache. Caveat: you still need authentication and audit logs. Isolation at retrieval is necessary, but not sufficient for full compliance. Next step: scale this exact approach by swapping the simple match scorer for a vector similarity, and then tune the number of neighbors returned to balance recall and cost. If practical AI engineering helps you, subscribe and watch the AI engineering videos.